All right, this is electronegativity and water. Just go ahead and write down what you see, and then we'll start here in 5 seconds. Okay, check it out. This is what makes water a polar molecule. Now, somewhere in your science background, you've learned that water is H2O, and that's great. And what is it literally, though? It's 2 hydrogens and 1 oxygen. And what happens is the O is in the middle, and you'll see it represented a couple ways, and we'll show it a couple ways here. The O is in the middle, and then it is covalently bonded or shared bonded to 2 separate hydrogens coming off from its core. And then we learned this bit about electronegativity. We know there's electrons from the oxygen and electrons from the hydrogen. They're all floating around everywhere. But we also have learned now that electronegativity is the ability to attract electrons in an atom when an atom is in a compound. And we also know that fluorine, on the top right corner of the periodic table, is the most electronegative element on the table. And we know that electronegativity decreases from this point. So fluorine is the most electronegative. That would mean chlorine and oxygen would be kind of the second most electronegative. And as you move further and further away, you could say nitrogen is less electronegative than oxygen. And you could even come over here and say that barium is less electronegative or has a less attraction for electrons than bromine or some of these nonmetals over here. And it kind of makes sense because we've learned that electrons want to gain electrons. Slow down. We learned that nonmetals want to gain electrons when they bond. And metals on the left-hand side of the periodic table want to lose electrons when they bond. So it would make sense that the nonmetals that want to gain electrons have a higher electronegativity or a greater ability to attract electrons in the compound. So with that idea in mind with electronegativity, the idea that oxygen has a higher electronegativity than, say, hydrogen over here, that would lead us to believe that the electrons cluster around the oxygen. So in this bond, the electrons have a greater attraction for the oxygen. And in this bond over here, the electrons have a greater attraction for the oxygen. So that means in this structure, this end of the molecule is said to be negative or have a negative end. This end of the molecule is said to have a positive end. So there is electron negative charge everywhere. It's kind of, when we say positive here, we're kind of saying absence of negative. Okay, so a cleaner way of writing this, you'll see it, is just as here's the water molecule, and oftentimes you'll see it in terms of some Greek symbol, and they'll go kind of goofy Greek symbol up here, and negative, and Greek symbol down here, and positive. Okay, another way they'll represent this is they'll just use circles. They'll use a solid, potentially a solid red circle for the oxygen, and 2 gray circles for the hydrogens. And again, they would say that this is the negative end of the polar water molecule, and this is the positive end of the water molecule. Right now, we want to stop this video and then do the Ed puzzle that accompanies this. And then after doing that Ed puzzle, we are going to draw this situation with NaCl dissolving in water. So I'll pause 5 seconds and then I'll continue. Okay, to recap here and to keep going, to show NaCl dissolving in water, we've got a big beaker And we've got, draw it a little bit different there, we've got NaCl, or a chunk of NaCl in our beaker. And we have these water molecules slowly dissolving the NaCl. And we know that NaCl is an ionic compound, and Na is a +1, and Cl is a -1. So as the water pulls these apart, we end up with Na plus ion, and then Cl minus ion floating around in the solution. And we know that the water is responsible for that, and we need to draw it in a definite, unique way, okay? So it would be beneficial to have two colors here. We have Na plus here, so it's a positive charge. Remember, positives and negatives attract, so the negative end of the water molecule is going to surround the Na plus, okay, notice the reds are with the negative end are snugged up around the Na plus ion in solution. And conversely, with the Cl minus, well, the positive end of the water molecule, or the side with the hydrogens, are going to surround the chloride anion floating around in the solution. So we would draw them kind of like this. So there's the positive end attracted that way. So here's another positive end attracted this way. And one more positive end here. So it's a subtle detail, but when ions dissolve in water, it's because the water molecule is polar, has a positive and negative end, and the positive end of the water molecule attracted to the negative chloride anion in this case, and the positive end, or the oxygen side, the negative end, the oxygen side of the water molecule, attracted to the positive cation in this situation. So we're able to sketch and represent an ionic compound dissolving in water.